Hello everyone, welcome to our webinar, Sentiment Analysis using Apache MXNet and Gluon. Our presenter today is Vikram Madan, who's a Senior Product Manager with AWS. We're excited to get started, just a couple of housekeeping reminders before we do. Today's webinar is being recorded and we'll send a follow-up email containing the on-demand links to the presentation deck and the webinar recording. Additionally, there's a Q&A window on your screen. Use this to submit any questions for our presenter and moderators at any time throughout the presentation so that we can take some of them live towards the end of the presentation. Without further ado, I'll turn it over to Vikram. Vikram, welcome. The floor is now yours.
Welcome, everyone. Thanks for joining us during this webinar. As mentioned, we're going to be talking about implementing sentiment analysis, and we're going to implement sentiment analysis with Apache MXNet and the new Gluon interface for Apache MXNet. The way this session is going to be structured is we're going to really walk through what sentiment analysis is, how to use natural language processing tools and other deep learning tools to really implement that. And then we're going to talk a little bit about the actual framework that we'll be using to do so. So let's jump in. So the story starts in terms of what is sentiment analysis. And basically, as I mentioned, it is a natural language processing task, and it classifies text or speech as some specified sentiment. And it's important, a couple pieces are important there in the sense that you are processing natural language. So it can be a text input, so something that is posted on social media, or a customer that is calling into your call center. You take that natural language, and basically what we're going to be able to do is connect that to some specified sentiment. And these specified sentiments are labels that you have created. Is it positive? Is it negative? Is it angry? Is it excited? Whatever those labels might be, they are constructed in the context of your specific objective. A little bit of more context here in terms of areas that sentiment analysis is used. The first is really understanding what people are saying about your brand. This is coming with the advent of social media, where there may be posts on a variety of different social outlets, say Twitter or Facebook, and you really want to understand, are people happy about the experiences that they're having with your brand, or are they not happy? Similarly, this can be extended to political sentiment analysis. There have been many presidential and other government official campaigns that really understand their constituencies leveraging sentiment analysis technologies. And then another major example is really understanding how your customers are feeling when they call into your call center, for example. These are some of the examples. Sentiment analysis is very extensible, and it can be used across a variety of different use cases. So moving on, we want to talk about basically the overall pipeline of implementing sentiment analysis. So we'll take this as a four-step process here. Up front, we'll talk about the labeled data that we're going to be that's going to be used for training. Then we're going to talk about how words are conceptualized in the context of machines and deep learning. How do we really translate these words that we're getting from as inputs from our customers or our employees, etc., and construct them in a way that they can start making sense in our analyses. Then we are going to understand how we want to train a neural network. And then finally, if you were to take this to the end, you would deploy this model for prediction purposes. So today we're gonna focus on the upfront pieces of constructing this model and training this model. But there's also a piece of, all right, once you have the trained model, let's use this to actually predict sentiments going forward. So the first area we're going to start with in terms of the data that we're going to be using in this example. We're going to be using the IMDb data set for movie reviews. And we're going to have two classifications for a movie review. Either it was positive or it was negative. So for example, you can see that this can become a pretty difficult task in some cases. In the sense of if you look at the positive side, that first review is not necessarily easy to decipher that it is positive. The impetuous pace of the film is at one with its moral shamelessness, and without thinking, we sign up for both. So there's a lot of negative words in there, but it is a positive review. The second one's a little bit more easy to decipher. What a magical movie. In the same way, negative reviews can also be a little bit difficult to parse as negative reviews. For example, in the first one, is a film so awe-inspiringly wooden. Awe-inspiringly is typically, a very positive sentiment type of word. But we're going to leverage deep learning and neural networks to really find a way to systematically determine which movie reviews are positive and which one are negative. And specifically, as I mentioned, we're going to be using the IMDb data set for movie reviews, and this includes 25,000 movie reviews. And remember, they can be of different lengths and different sizes, different number of words. But there are 25,000 of them in total, and 12,500 of them are labeled as positive, and 12,500 of them are labeled as negative, so a 50-50 split. And these actually have been labeled positive and negative by humans. So this is a very important aspect broadly across deep learning in the sense that you need a labeled data set. A lot of this is learning in a supervised manner. You feed data that that you have established the truth around, and you feed that through your deep learning model. But in that is overall the data that we're going to be using, and it is the use case that we are going to be exploring. So let's move to broadly understanding how to make words understood by machines. And kind of the important thing here to understand is that there's been a lot of research and a lot of advances in this space. And two of the primary approaches to attack this problem have been word-to-vec, and glove. So the first one obviously stands for word to vectors, and the second one stands for a global representation of word vectors. And basically what this does is it takes a large input, imagine, and what is called a corpus. So in this case, it is all of Wikipedia. And it leverages that and it studies that to develop vector representations of each word. So let's kind of explore that a little bit more. So this within itself, understanding how words relate to each other, is a massive effort within itself. And in the context of leveraging that large corpus of words, basically what you're looking at is co-occurrence of words. And what that means is that which words occur close together. And leveraging insights built on that co-occurrence to understand then what types of words are similar to each other. So in the American football context, you might have a receiver or a player, a wide receiver, for example. In those contexts, those words are very similar together. Like I threw a ball to the player, or I threw a ball to the receiver. And in that case, ideally, what the output that should come is that we can figure out that the receiver and player are very similar words in this context. They should have a vector representation that puts them very close to each other, because they will be surrounded by similar types of words. The quarterback throws it to the player, the quarterback throws it to the receiver. In that case, what you have then, based on that co-occurrence analysis, that you can build out a vector representation of this. And it's important to understand this a little bit also. You can see on the right-hand side, we have given you kind of a representation of these vectors. So you have your full vocabulary, kind of each word, obviously start with aardvark, which is the first word in the dictionary, and go all the way to the end. And this again depends on your specific use case, and you can constrict it and decrease it as necessary. But imagine you have the capacity to handle all different words. And then you have a separate dimension, which is the d-dimensional vector that is associated with each word. And that is going to essentially allow you to systematically capture the richness of the word. So the larger your dimensionality is, the more richness that you can capture. But that specific vector, which each word will have its own numerical values in each of those slots, will essentially define the word from a machine perspective. So let's kind of play that one step forward and look what that means. So as I mentioned, we're going to look at the co-occurrence of words, right? And in this case, on the left-hand side, you see a simple sentence, the quick brown fox jumps over. And in this case, when we were building out this model to understand words, we are essentially going to look at a window around the word. And in some cases, we can discount the farther away a word is from within that window, right? So in some cases, if you take the quick brown fox jumps, right, the brown is closer to fox, whereas brown is further away from jump. So in that case, we'd actually give more credit to the brown and fox relationship versus the jumps and brown relationship. But based on this, leveraging kind of this programmatic way of understanding words, you get to these output vectors. And in some cases, you can see actually this is the glove word embedding, and it's 6 billion words, and that's what the 6 billion stands for, and it's 300 dimensions. So the dimensionality vector is 300 units long. So obviously, this picture, which is only two-dimensional, is just a kind of a condensed representation of those 300 dimensions. And you can see basically, all right, now we are looking at foods, right? So basically, you have bean, artichoke, chive, dill, chowder, etc. And these are all kind of aggregated near each other in the overall vector space. And how that kind of came about is you kind of see in this context, if you have these words, and we're kind of breaking a separate sentence, the Cardinals will win the World Series after considerable deep learning kind of applied to it. You have these individual vector representations. And this is an example, just to clarify, this is a three-dimensional vector here. So the word the corresponds to a vector with these three values. The word world corresponds to a vector with these three values. And now when you plot these three values, you should see this word kind of aggregating closer to words that are similar to it. So moving on, here I want to talk about glove specifically because this is actually what we will be using in the model. And I mentioned in the previous slides, that there's a learning process. You actually have to feed a giant corpus into a deep learning model and understand the vector representations of the word. What about if I could tell you that we're actually going to skip that step because someone's already done the work for us? And that's exactly the case. So the global vectors for word representation, or GLOVE as it stands for, is a Stanford project. And basically it has leveraged a very, very large corpus and that co-occurrence plus a little bit of a decay factor applied for words that co-occur actually at farther distances from each other. And it has essentially learned that very, very large vocabulary size of words and has given us those vectors to use in our model. So we actually don't have to learn that from our own corpus. We can just leverage this GLOVE word representation off the shelf and move quickly. There's a variety of different research, and this is kind of a broader meta point in the sense of you can use there's a variety of different research, and this is evolving kind of very quickly. You're welcome to use word to vec versus GLOVE. You're welcome to use GLOVE over word to vec, but there's different preferences for each one depending on what your use case is. But generally, in this case, what on the Stanford slide is that GLOVE performs better on these different tasks than the CBOW, which stands for continuous backed words, or the skipgram representations for word to vec. Those are both components of word to vec, so that's kind of one data point, and then GLOVE is shown there. And basically, those are two different use cases: the semantic and the synonyms, and you see the total accuracy as well. So basically, here, again, we will be using GLOVE in the context of our model. This allows us to focus not on the whole massive task of building word representations, but rather analyzing the sentiment of our input data. So moving forward here, let's talk generally about deep neural networks. And I'm not going to go too in depth here. I'm going to assume a little bit of understanding. And you're welcome to kind of maybe reference outside materials at this point. But at a high level, I think the number one thing that I wanted to call out with deep learning, deep neural networks, especially kind of what are the more simplistic multi-layer perceptrons and your convolutional neural networks. In these cases, often you're primarily dealing with fixed inputs. Say a picture. It's a singular input and there's no kind of time-based series nature of it. So it's a fixed input, it's fed into the model, and you get some output on the back end. You feed in a cat picture and you get that it is 90% probability that is a cat, 10% probability that is a lion, something to that effect. But basically, the input here is fixed, and there's no sequential nature to it. And so that's very important to understand why we are going to be using the model that we are going to be using from a deep learning perspective. Specifically, we will be using a long short-term memory model for doing our sentiment analysis. And we will not be using the typical fully connected layers in that context. So moving on, we want to move from deep neural networks to recurrent neural networks. And the important piece here is with recurrent neural networks, this is very important in the context of using to understanding sequences and understanding essentially what has happened in the past to make our decision at this point. In this case, you can see this is very important for an NLP use case. And right here, what you're seeing is the movie was, right? Those are the first 3 words of some review, let's say. And in this case, you can see each word, there's some weight applied to it. And that's associated, that weight is not specific to the word in any sense. It's specific to the time, the T that that word is at. So the first word has a weight associated with it. The second word has a weight associated with it. That each feeds into this hidden state. And the important thing you need to recognize here is that the hidden state is very important in this context because it is our record of what has been happening throughout the past. And this is, in this case, the past is the previous words. So it is kind of your memory, if you will. Whereas the weight that is applied to each word is specific to that time. The H is basically and incorporates. It is the output that takes in the value at that time. So at time T, it takes in movie, but it also takes in everything that has happened at the past. And that's the very big thing to realize around recurrent neural networks. It's very important for handling sequential type of inputs, which kind of a movie review in the natural language processing context is. And then it leverages that memory to make a more informed decision of what exactly that the output is. Let's take it one step further and understand what differentiates a long short-term memory network over a recurrent neural network and just a general deep feed-forward neural network. As you can see, what I tried to show here is that these each build upon each other. The important thing here is that the LSTM works very much like the simple recurrent neural network, and it is essentially a type of the simple recurrent neural network. And you can see that there's a similarity here in the sense that the xt minus 1, xt, and they all feed into this state. And similarly, you can see there is a hidden or memory state that is pushed out. And the memory state is kind of pushed out at each cell of the LSTM, but it's also fed into the next cell. And that way, that output of HT plus 1 also incorporates HT as well as XT plus 1. The important thing here is that long short-term memory networks have been shown to preserve long-term dependencies well. Meaning, if you have a sentence where this movie was really good, I didn't really like the ending, but it kept me in my seat throughout the movie and was a good experience, right? So you have 3 sentences. The first one's positive. The second one is slightly negative, and the third one is positive. So positive, negative, positive. It allows you to understand that, all right, if I only see kind of the most recent history, the second sentence and the third sentence, second one being negative, the third one being positive, I'm a little bit more unsure of exactly what the overall sentiment of this movie is. Now, if I keep a long-term dependency, if I understand the long-term dependency, that first sentence started off overly positive, then I can make a more informed decision as to whether this is a positive or a negative sentiment. And in that case, overall, you and I can tell that, hey, this person actually likes this movie. Maybe they were a little bit disappointed by the ending, but overall, I think they would recommend this movie to their friends. And that's kind of where we want to get to with this use case, right? So net here is that LSTMs are really good at preserving those long-term dependencies, and it essentially at a high level, there's a lot of theory around this. So I strongly recommend kind of diving deep into those areas outside of this context to understand that, but there's leveraged this gating concept that essentially you can learn when to lock a gate or unlock a gate. And in those gates are these longer term dependencies. Um, and to help conceptualize all of this, I found this example developed by an individual named Edwin Chen. You check out his blog. I found it was very, very useful to even help me understand kind of this. And it's a fun example, especially if you enjoy these things. But this is a Snorlax, and basically this is kind of a Pokemon character. But it's a great representation of what's the difference between a simple neural network, a recurrent neural network, and then a long short-term memory network. So in this context, what you can see on the left-hand side with this simple neural network, I see the Snorlax and water, and he's probably taking a bath. So basically, it's a very simple, simple kind of analysis, and it actually predicts what is happening. Because in actuality, the Snorlax is in this context, in this sequential context, because it's moving a little bit away from natural language processing into kind of video frame by frame analysis. But they're very similar types of problems. Regardless, what we know in previously is that there's another kind of creature that is attacking this creature. And so we know that that this is actually predicted wrong, right? It predicts that he is showering at a 0.6 ratio or 60% probability that he's showering. In actuality, he's being attacked, which predicts 10%. And this is because it's understanding the picture, it's understanding this singular context, but it doesn't understand what has happened sequentially before. I think that's kind of one of the big elements of why recurrent neural networks are so important in terms of understanding sequential data, because they incorporate that historical long-term dependency in your analysis. So now let's move to understanding recurrent neural networks. And here there's some hidden state that has, and what we call memory, that has been initiated and that you leverage before you start analyzing. So you can see in the first cell, the memory that is being fed in is that a battle scene has started. And in this context, you know that there's a battle scene. You see water coming out of this Pokemon's mouth, and it is probably attacking in this case. That is the assessment you make. And with that assessment, you know that there's an 85% probability that that is happening. That's what your model outputs. And then the other stuff is a little bit a lower probability. The hidden state that's passed on to the next cell is that in this battle, the enemy has launched the attack. The enemy is a water Pokemon. So, that memory, that context is passed on. And at that RNN cell, you say, I remember we're still in a battle scene, and I see that there's water coming at this creature, and then he's probably getting hit. So with that, you essentially see a probability of 0.6% that he is being attacked. The other probabilities are much lower. And similarly, the hidden state is passed along. Now, if you go one step further and you leverage the LSTM here, there's long-term memory that you are continuing to store. The Snorlax he likes bamboo apparently. And then there is, you're 1 minute into the battle scene and the enemy is in the center of the screen. The working memory is kind of the shorter term, what has happened in the most recent past. But basically, when it comes to the LSTM essentially says, what should I forget? The enemy Pokemon's location on the screen, and then what should I save? The Snorlax look of pain, so you understand kind of there is something bad happening here? And then what should I ignore? You don't really care about that long-term memory piece in terms of that he likes bamboo. So you can kind of siphon off the noise there. And that's very important because if you look at the probabilities above, you do see an increase in the probability of understanding that he is being attacked at 0.9%, sorry, 90% versus the 60% that we saw on the previous page with the simple recurrent neural network. So now I want to talk about the tool that we'll be using. Specifically, we are going to be using the Gluon API. The Gluon API specification, which was actually released in early October, and it was a joint effort across Microsoft and AWS. And basically, it provides a higher level interface, so it's easier to use. It's a fully imperative interface that provides greater flexibility in terms of how the neural networks are constructed. And also, it allows you to achieve high performance very easily when you are training your models. This is very important because training is a very computationally intensive process. You want to be able to easily move from an experimentation phase to kind of being able to train your models at scale easily. As I mentioned, Gluon was developed jointly by Microsoft and AWS. It has to be implemented in the individual framework. So it is part of MXNet, and we'll be using MXNet for the code sample. And then we will, it will also be released in the Microsoft Cognitive Toolkit at a later release. And then we expect this also to be picked up by other frameworks. It's not kind of limited to just these frameworks. It's meant to be kind of a broader API specification that we think would bring value to a lot of different deep learning frameworks. So quickly, just wanted to go over the different aspects in one more layer of depth. The simple, easy to understand code, basically, this provides simple, clear, and concise code, and you can leverage that code to define your neural networks. They're essentially plug and play building blocks. As I mentioned, the flexible imperative structure, it eliminates this need to have a rigid neural network structure. And it brings together the algorithm used to train as well as the neural network structure itself. That leads to benefits like easier to debug. The code is more familiar because it's all Python-based code when you develop your training loop, for example, and it's all intuitive. Dynamic graphs are kind of a major development in the natural language processing space. That essentially means that your models, your neural network models, can be constructed on the fly during the train process. So for example, there's a tree-based LSTM model which reconstructs the neural network on each pass, and that's kind of enabled by fully imperative interfaces like Gluon. As I mentioned in the previous slides, that Gluon also enables high performance when it comes time to train your model with the full heft of all of your data. Basically, you can do all of your experimentation and then flip a switch very easily, moving to the high performance kind of engine of Gluon. Very quick code samples here. As you can see, this is a simple neural network with 2 hidden layers. These are fully connected dense layers, each with 256 nodes and an activation function of ReLU. It is initialized, and then you specify the layers. So very simple, concise code. Then we have the fully imperative structure. Basically, this is clearly demonstrated that your training loop essentially can be a nested for loop. So it's Python native code, what you're doing here is basically you are computing the output of the data. With the output equals net, and net is your model. You calculate the loss. You do the backward propagation step, which tells you how well your parameters are decreasing that loss, and then you update your model parameters accordingly. So very simple, intuitive syntax. And then finally, dynamic graphs. Here I show where you can define how your graph is constructed on each forward pass of the model. And then finally, we have the high performance piece, where basically you can imagine as simply flipping a switch. So here we've made a small adjustment to the definition of the model. We make it a hybrid sequential, and that essentially allows us to call this net.hybridized method, which allows us to get a lot of the performance benefit under the hood. So barely have to change your code when it comes time to get that performance bump, because you're ready to throw the mass of your data. So with that, we talked about sentiment analysis and how to implement it, and we talked about the tools that we're going to use to implement it. All right, now I'm going to walk through the demo, which is actually a full Jupyter notebook that has implemented sentiment analysis, and just explain to you each of the different pieces, and you're welcome to kind of explore the notebook in detail on your own time. But here, basically, we're importing all the required elements that we need, and moving on, we pull the data in. And here, we're actually using Stanford's large movie review data set, which is actually the IMDb data set. It includes those 25,000 different reviews, half and half, which are positive and negative. We're basically doing some basic data manipulation to save those into the way that the model is going to process them. We create a function to clean the strings. So basically, we're removing any non-word elements. So we want to be able to kind of pull in the words cleanly of the review in order to be able to make the determination whether it is a positive or a negative review from that perspective. Here, we're starting to essentially create an accounting of the words that we're seeing in all of the reviews. That's going to basically help us determine which words we're going to pay attention to, and in the context of when we set the total vocabulary size of the model. So we can't, just from a kind of limitations perspective, it's not efficient to look at every single word that we see. We're going to have to cut it off at a certain point. We're going to do that in a smart manner by essentially counting the number of instances of each of the words throughout the whole corpus of all the reviews, and then order them by the most likely occurring words, and then cut off at a certain point where we want to, where we determine the size of our vocab. Here, we are essentially encoding the sentences. So basically, we are finding the words. We are representing them with a number just to allow easier processing. And we also create a function to pad the sentences. So this is important in this context where we are limiting the size to actually 500 for each review. So some reviews might be longer, some might be shorter, but we are limiting the total number of words to 500. If it's less than 500, then we pad the words that are that are between the number and 500 with the value 0. Here we bring them together, and we're now ready to kind of take this and process these reviews. We set our vocab size to 5,000, so any word that exists in our word count but is ranked 5,000 or below, we will just mark as 4999. So in that way, that is just kind of a word that it is an unknown word, if you will. Now here we pull in the glove index. So we've created kind of our word vocabulary that's relevant to our the data that we're analyzing. And now basically we need a way to represent those words as vectors. We can learn this actually independently, but we're going to leverage something off the shelf here. And as I mentioned, we're going to leverage Stanford's global vector for word representation, embedding. And the output here is this embedding matrix, which takes in all the words that we are tracking and enriches them with the vector representations that we take through essentially this glove. We create our test and training data set here, and basically, kind of moving on, we are ready to analyze this data. So the first thing that we're going to do here is we are going to use Gluon. So all the steps that we did actually to this point, which is the vast majority of this notebook, is actually pre-processing, just getting the data ready to feed in. The first thing that we're going to do with Gluon now, and to demonstrate the simplicity here, that we are essentially defining a simple neural network with a handful of lines of code. We have the embedding layer here. We have the LSTM layer here. You see the number of hidden. This is the number of cells for the LSTM. And the embedding size is essentially the vocab size. So the number of words are going to be on that. If you imagine that that matrix that we saw before, the vocab size is going to be the Y dimension, and the number of embedding, that's essentially the dimensionality of the vector, that's going to be your x-axis, right? So in this case, it's 300 dimensions by the 5,000 word vocab size. And here we have, as you can see here, we have 64 hidden cells. This is the 64 that we are plugging into the LSTM. And then finally, we have the dense layer at the end to actually do the classification process for us. We only have two classes here, right? The first class is positive, the second is negative. So at the end of the day, we need to get to that classification at the end. Here we have the evaluation function. So we're going to leverage this in the context of a training loop. Basically, you feed in the data, and we are going to calculate the output of the model, and we calculate the predictions, and then we compare the predictions with the ground truth, and that gives us the accuracy of what we're seeing. Now, what we're coming to with kind of setting up, doing the initialization and then setting up the training loop for Gluon, we have the initialization for the parameters. This step helps us actually set the embedding matrix that we've created. So this is the step that says we're going to use glove now versus actually creating this from scratch through this training process, which is kind of a pretty massive effort in itself as well. We initialize the trainer function. This is the optimizer. This is what's going to help us converge on the predictive model. We feed in the model parameters here, which have been initialized up here. We indicate that we're going to use stochastic gradient descent, and we define the learning rate. The learning rate is a hyperparameter that you can determine. We've set the learning rate up here to 0.001. This is essentially the rate at which the model learns at each pass of the training process. We're going to use soft max cross entropy loss here, and you see us kind of implement that here in the training loop. Now we are ready to talk about the training loop here. Basically, we have the number of epochs as your outer for loop, and we have kind of working through each of the number of batches in the inner loop. So basically, you can come back up here and you see we're actually going through 10 rounds of the data, 10 epochs, and your batch size is actually 12 in this context. Here we get the data and the target, and then we feed that into this essentially 4-step process for each batch, right? So we calculate the output of the model. We calculate the loss, which is our objective function. It helps us understand how the model is performing. So it leverages the output that we calculated here and what the target is. The target are those labels, right? Whether these reviews were positive or negative. We do the backward propagation, which essentially determines whether it determines how the model parameters are affecting the loss, right? So it helps us understand which model parameters are actually increasing accuracy the most or decreasing loss the most. And based on that, we do the trainer step that updates those model parameters accordingly. We have the test and train accuracy that you calculated here. And basically, you can see the results of the first epoch. This is a very kind of data intensive model, so it will take some time to run. But basically, you can see that is the output at the end of it. And with that, I welcome you to kind of dive deep into this notebook and let us know if you have any questions. Thanks.
Awesome. Thanks so much, Vikram. That was a great presentation with an awesome demo as well. We're going to be transitioning over to the live Q&A format here as mentioned. Please take a moment to submit some feedback at the polls you see on your screen. Additionally, if you have any other feedback for us, please drop us a line at aws-webcasts@amazon.com. Vikram, back over to you.